space isn't only bright with stars, it's also rich with quiet. Far beyond our sky lies a giant stretch of almost nothing, called the Boötes Void. Imagine an empty room in a crowded city, dark, wide, and strange. Why is it there? How did it grow so big? And what can its silence teach us about the rest of the universe? In this episode, we'll drift slowly into that emptiness, meet the few lonely galaxies holding their light, and use their glow to explore gentle ideas about gravity, the subtle push that makes space expand, and our distant future. If calm trips through the cosmos help you unwind, tap like and subscribe so you won't miss the next journey. Settle in, breathe easy. The story begins in the quiet between the stars. In the constellation Boötes lies a region so wide and bare that even whole galaxies are scarce. Astronomers call it a void, which simply means a place in the universe with far less matter than average. This one is the Boötes Void. It is not the usual empty space between stars, or even the normal gaps between galaxies. It is a vast stretch where galaxies themselves are missing. The idea alone pushes against our picture of how the cosmos is built. In 1977, the astronomer Robert Kirshner and his team surveyed this area and found almost nothing. No soft fuzz of faraway galaxies, no clusters, not even the thin glow of scattered dust, just darkness reaching on and on. At the time, many models treated the universe as fairly uniform on very large scales, with matter spread out like city lights seen from a plane at night. You expect gaps, but not a great black neighborhood with almost no lights at all. The Boötes Void forced a pause. If the universe grew from tiny ripples after the Big Bang, how did a smooth picture produce a hole this large? Scale helps. The void spans about 330 million light-years across. Light, the fastest thing we know, needs roughly 330 million years to cross it. Imagine an empty parking lot placed in the heart of a crowded city. This lot would be bigger than the city, then the state, then much more, until the comparison feels too small for the job. It is a region where, for reasons we need to understand, matter did not collect into bright island universes the way it did elsewhere. The discovery drew careful attention, not shock. Astronomers asked steady questions. Did the matter here never gather? Was it pushed out by flows from surrounding regions? Are we looking at a normal feature of the cosmic web, simply scaled up, or something that asks for new physics? The place earned nicknames the Great Nothing, the Cold Spot, but the work that followed was patient. Deeper surveys confirmed the emptiness. This was not a simple gap between clusters. It looked like a true, low-density bubble in the large-scale structure of the universe. As maps improved, something even more interesting appeared. The void had shape. Its edges and interior were not random. And inside, against expectation, a small set of galaxies shone like islands in a dark sea. Theory said a region this large should host on the order of a couple thousand bright galaxies. Instead, early counts found only 8. The contrast is a useful image. A concert hall built for 2,000 guests, with only a handful of people seated far apart, each lit by a small pool of light. Most galaxies do not live alone. They gather in groups and clusters, trading gas, sometimes merging, growing heavier elements over time as stars live and die. The Milky Way is part of such a community. Our nearest large neighbor, the Andromeda Galaxy, is only about 2 million light-years away. In the Boötes Void, isolation is the rule. A void galaxy might sit 50 million light-years from its nearest peer. That distance stretches interactions thin. With few close encounters, star formation stays slow. Without a steady supply of fresh gas and without the stirring that comes from collisions, these galaxies often remain small and dim. Their light shows fewer metals. Astronomers use this word for elements heavier than hydrogen and helium, a clue that their stars have had fewer cycles to forge and spread heavy elements. The environment has shaped them. Researchers give this overall pattern a simple name: underdensity. It means less stuff than average, and it matters because gravity follows the stuff. Where matter is thick, gravity pulls more in. Where matter is thin, gravity has less to pull with, and material tends to drift away toward denser zones. None of this is spooky. It is the same physics, but played out over hundreds of millions of light years. Still, the size and purity of the Boötes Void make it a strong test. By chance alone, getting a patch this empty is very unlikely. So models have to explain how such an underdensity grows and keeps its shape over time. The 8 early survivor galaxies added another puzzle. They are not scattered. They line up as a tube, what cosmologists call a filament, threading across the void. A filament is a long, thin bridge of galaxies and dark matter that connects denser regions of the cosmic web. Picture an invisible tunnel that runs hundreds of millions of light years, with a galaxy every few tens of millions of light years along its length, each one like a quiet station on a night line. In most places, many filaments cross and feed clusters. Here, a single pale thread stretches through open space. Random placement is a poor fit for this neat line, so scientists look for structure. One idea is that the filament is a fossil from an early time. After the Big Bang, matter was not perfectly even. It collected along ridges and walls shaped by dark matter, the unseen mass that outweighs normal matter and guides much of the universe's large-scale pattern. If an ancient dark matter strand passed through this area, it could have seeded a small chain of galaxies, even while the wider region stayed thin. As the universe expanded and matter elsewhere clumped more strongly, this thread would fade but not vanish, leaving a ghostly line that we can still trace. The galaxies in the strand offer clues. Their motions, measured by tiny shifts in their light, tend to point along the same general direction, as if they are following a shared current. Their spectra show fewer heavy elements than similar-age galaxies in busier parts of space. These signs match the story of a quiet upbringing in a low-density zone. Fewer mergers, fewer shocks, fewer chances to recycle starlight's ashes into new, metal-rich stars. Perspective also plays a role in how empty the void looks. Seen from the side, the filament is a thin streak across a dark field. From many angles, those few galaxies blend into what seems like a single point. The human eye and brain like to fill gaps. Here, there is little to fill. The scene stays spare. There is another property of voids that helps explain their growth. On average, the universe expands because of dark energy, a term for whatever drives space to stretch faster over time. In underdense regions, that stretch can outpace the cosmic average by a bit. You can think of a void as a low-lying patch in a map of density, except the downhill leads away from it. Matter flows toward heavy structures. The void is left behind, and the space inside grows emptier. This is sometimes called void instability. Once a patch is underdense, it tends to become more so. Models and measurements suggest that the Boötes Void expands slightly faster than the general Hubble flow, often described as on the order of 10% faster. Over millions and then billions of years, small differences add up. A picture forms. The Boötes Void is not a tear in the universe. It is a natural outcome of gravity and expansion, acting on an early pattern. What makes it special is its scale and cleanliness. It shows how the cosmic web builds itself. Dense knots grow denser, thin regions thin out. The few galaxies that grew inside the void are useful laboratories. They let us watch how isolation changes a galaxy's life, its size, its star formation, its chemistry. They also trace whatever hidden structure runs through the dark, whether that structure is a relic filament of dark matter or a more complex shape. There is still room for questions. How exactly did the void reach its present size? How smooth is its interior once we sample fainter and smaller galaxies with deeper surveys? Do the motions of the strands galaxies reveal a precise map of the underlying mass? Or will new data show bends and branches we have not seen yet? Some estimates even project that, if current trends persist, the void could roughly double its size over the next few billion years, a reminder that the large-scale pattern is still evolving. The 8 survivor galaxies will drift even farther apart, their quiet neighborhoods growing wider and darker. The pace of that spreading hints at more than ordinary expansion. The region is not only riding the general stretch of space, it seems to be pushing matter away on its own. Dark energy, the name for whatever drives the universe to expand faster, appears to have a stronger effect inside the void than outside it. That extra push acts like a soft vacuum, lowering matter density and keeping it low. Some theorists describe a more radical picture, a bubble of false vacuum. In simple terms, a vacuum is the energy of empty space. A false vacuum would be a higher energy state that isn't truly stable. If a patch of space slipped into such a state, the rules inside could shift slightly, and that patch could swell faster than its surroundings, driving matter toward its edges. It is a working idea, not a proven one, but it shows how unusual physics might take root in a place already lacking mass. The faster stretch shapes what we see from Earth. Light from the few galaxies inside the void is redshifted more than expected, its waves pulled longer by the extra expansion. That added stretch makes those galaxies look dimmer and farther than they truly are. Even without new forces, this fits a simple picture. Where matter is thin, gravity's pull is weak, so space can expand a bit more freely. Over long times, small differences in expansion build up into clear effects. The emptiness does not end sharply in the sky, but its influence gathers at the boundary. Around the edges of the Boötes Void, galaxies crowd into great walls, as if drawn together by the same flows that leave the center bare. These walls can be several times richer in galaxies than typical regions. The contrast feels like standing in a wide room where most people hug the walls, leaving the middle open. In space, that crowding forms filaments and sheets, long chains and broad planes of galaxies that outline the void like a frame. Some wall segments pack in far more galaxies than a similar volume elsewhere would hold. The change from crowded to empty can happen over a zone only a few tens of millions of light-years wide. On one side, normal cosmic traffic. On the other, quiet. Simple models of gravity favor smooth transitions, so a cliff-like drop in galaxy numbers is a strong clue. Either the initial underdensity was unusually deep, or extra physics has helped maintain the edge. Motion adds to the story. Galaxies in the walls show speeds that are hard to explain with gravity from visible matter alone, as if they feel a mild shove away from the void's interior. In the language of physics, that points to a pressure gradient, a push from lower density toward higher density, stronger than models easily produce. Light crossing the walls also carries fingerprints of the structure. Gravity bends light, a phenomenon called lensing. Here, the effect is subtle. galaxies behind the dense regions look slightly sheared or stretched, as if seen through a gentle funhouse mirror. Closer to the boundary, some small groups seem to be slipping inward. Their shapes look pulled, their star formation uneven, like taffy being drawn out. Tides, differences in gravitational pull across their sizes can do this, especially near sharp gradients in mass. To understand how such features can form and endure, the story reaches back to the early universe. In the beginning, space held tiny ripples in density quantum fluctuations, blown up to cosmic size. Most were only a few parts in 100,000. Over time, gravity amplified the peaks and drained the valleys, moving matter from underdense patches into overdense ones. Voids are the natural result of that flow, but most are modest. The Boötes Void stands out for its scale and its clean interior. Simple pictures compare gravity to a landscape of hills and basins. Matter rolls toward basins where density is high. A deep, wide basin grows deeper as more matter falls in. A broad, high plain grows higher as matter leaves. In a strong void, the slope away from the center can be enough that material prefers to stream outward rather than wander back in. Add the overall stretch of the universe, and the interior thins further. If dark energy acts a bit more strongly there, or if the underdensity reduces the breaking power of gravity more than average, the net result is a region that empties faster than its surroundings. There are several possible reasons for an underdensity this extreme. One is that dark matter, the unseen mass that makes up most of the universe's scaffolding, may be particularly scarce inside. Galaxies grow where dark matter halos are dense. Without that framework, normal gas has a harder time cooling and clumping. So few galaxies take root. Another idea reaches into the very early phase transitions of the universe, when conditions changed rapidly, like water freezing into ice. In such transitions, small patches can get stuck in a different state. If the void sits in a patch like that, its properties could differ enough to slow the buildup of structure for billions of years. Maps of ancient light, the cosmic microwave background, add a clue in the same general direction. In the area of the Boötes Void, the background shows a mild cold region, a signal consistent with an underdense line of sight affecting the aging of light as the universe expands. This does not prove a direct one-to-one match, but it supports the idea that the underdensity is old. Simulations that start with ordinary ripples rarely yield a void this big by chance alone, which is why researchers test optional ingredients, unusual initial conditions, a different growth history for dark matter, or regional differences in how dark energy acts. Space-time itself carries the mark of the void. General relativity ties gravity to the curvature of space and time. Dense regions curve space inward. Light and matter follow those curves. In a very empty region, the curvature flips sign, forming a shape more like a saddle. Photons passing through experience a slightly different path than they would in an average patch. The outcome looks like a gentle anti-lens. Background objects appear a bit dimmer and more spread out than they otherwise would. The signal is small, but measurable, with careful statistics. Time also runs at a slightly different pace in weaker gravitational fields. In practice, clocks inside a deep void would tick a touch faster than clocks in a crowded cluster. The difference is tiny, far beyond everyday experience, but it follows directly from the theory that has passed every test we have thrown at it. Ripples in space-time gravitational waves should also feel the change. As they cross an underdense region, their amplitude and frequency shift in minute ways. Future detectors, designed to watch wide patches of sky and long stretches of time, could use those shifts to map the three-dimensional shapes of large voids, much as lensing maps mass along a line of sight. There is also a clean observational effect tied to underdensity and expansion. As light climbs out of a region with less gravitational pull and into the broader, expanding universe, it can gain an extra redshift on top of the usual stretching from expansion. In large-scale studies, this is related to the integrated Sachs-Wolf effect, light picking up or losing energy as it crosses evolving structures. In a void like Boötes, the sign and size of that extra shift help diagnose how fast the region is changing and how strongly dark energy is acting there. Beyond standard ingredients, some models entertain more exotic possibilities. If a patch of space held a form of energy with unusual pressure, sometimes described formally as negative pressure that could strengthen the repulsive behavior we infer, fields like this are hypothetical in the present-day universe, and any real signal would need strong, independent evidence. Still, the void is a place where such ideas can be tested because the background noise from ordinary matter is low. Particles that travel almost at light-speed cosmic rays also respond to the shape of space-time. Paths through a broad underdensity can bend in ways that produce faint shadows or offsets in where the particles seem to come from. Those paths, together with lensing and redshift patterns, feed into a single picture. The void influences not just what is inside it, but also signals that pass through and around it. The reach of those effects extends well beyond its visible boundary and touches the ancient light that washes over the whole sky. The Boötes Void leaves a faint mark on the oldest light we can see, the cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang, set free when the universe was about 380,000 years old. Across the sky, it is almost the same temperature everywhere, with tiny ups and downs that trace the first small differences in density. In the direction of the Boötes Void, those maps show a broad cold spot that spans several degrees. The temperature dip is tiny, roughly 30 millionths of a degree, but it stands out because large, smooth features like this are rare. This cold patch tells us that the line of sight through the void has been underdense for a very long time. The main process behind the signal is called the integrated Sachs-Wolf effect. In plain terms, light loses or gains a little energy when it crosses regions whose gravity is changing as the universe expands. If a region thins out with time, like a void that keeps emptying photons climb out with a touch less energy than they had going in, their wavelengths stretch a bit more, and the CMB appears slightly cooler there. You can picture it as a gentle toll. The light pays a small energy cost while passing through a place whose gravitational pull is fading. Because we can measure the size and the depth of the cold spot, we can work backward to learn about the void's past. Computer models start with an early, mild underdensity and let it evolve under gravity and the general expansion of space. Those runs tend to produce a region that grows emptier over billions of years and carves a cold signature into the CMB along the way. One puzzle remains. In standard models, the temperature dip should be larger than the one we see. The observed depression is roughly half as strong as many calculations predict. That mismatch could mean that our models of void growth need adjustment, or that extra effects partially fill back in the cold imprint. Several possibilities sit on the table. Warm gas along the path can add a bit of energy back to CMB photons, softening the cold spot. Small-scale motions and magnetic fields can also stir the gas and change how the light is scattered. None of these ideas are final answers yet. They are ways to test where the missing piece may be. The angular size of the cold spot, how wide it looks on the sky, helps in another way. By comparing that size with the typical distances at the void's redshift, astronomers can infer the geometry of the empty region. The current best fits say we are looking almost face-on, seeing something close to the void's full to 300 million light-year span rather than just the edge. Other voids produce their own faint cold spots, but the Boötes signature is larger and cleaner than most. That is one reason it attracts attention. It offers an independent handle on big-picture physics. The pattern of temperature across the sky is sensitive to dark energy, the driver of the universe's accelerated expansion, because the ISW effect only shows up when the expansion rate changes how gravitational wells and valleys evolve. The cold patch in the Boötes direction is consistent with a universe where dark energy matters. Its exact depth and shape help set limits on how strong that effect is. The same data can check details of inflation, the very early growth spurt that laid down the first tiny ripples. Maps of galaxies give a closer view of what the void looks like in 3 dimensions. Deep surveys show that the Boötes Void may not be a single smooth bowl. Instead, it appears to be made from several smaller empty regions that have merged. The picture is like 3 or 4 soap bubbles drifting together and becoming one larger bubble. Over time, smaller voids expand and overlap. Their edges meet, and the interior becomes one broader underdensity. Each original bubble carries its own history, so the merged whole can hold subtle differences from place to place. Clues for this come from where the few galaxies inside the void actually sit. They are not sprinkled evenly. They clump into small knots and thin lines, as though outlining old boundaries between the component voids. The narrow tube, traced by the 8 bright survivor galaxies, makes sense in this view. It could be the seam, the interface, where 2 large empty regions once met. At those seams, the leftover matter is most likely to gather, and that is where small galaxies can form and persist even while the wider field remains bare. Simulations support this merger story. When models begin with multiple modest underdensities in the early universe, they more naturally produce an elongated shape with sparse filaments and knots inside, closer to what we observe, than models that start with one giant empty patch. The merger path also helps explain the void's present expansion rate. When several voids join, the combined region inherits the push from each part, so the net evacuation proceeds faster than any single component would manage on its own. The timeline written in the light of the void's few galaxies adds more detail. Spectra rainbow-like splits of their light carry information about the ages of their stars and the amount of heavy elements they contain. In the Boötes field, those indicators show small gradients. One sector holds galaxies that look a bit older and poorer in metals than those in another sector. Metals, in astronomy, means any element heavier than helium. Lower metal content hints at fewer generations of star birth and death. If the northern slice is older and more metal poor than the southern slice, that suggests the northern component void formed a little earlier and kept conditions quiet for longer. The southern part may have stayed denser for a bit more time, giving its few galaxies an extra chance to enrich their gas before they, too, were left alone. Radio observations add another layer. Several of the void's galaxies show radio jets, lobes, or halos with odd shapes, as if the environment changed around them more than once. In a merger picture, that makes sense. During the joining of voids, the thin gas at the interfaces can flow, compress, and relax in steps. A small galaxy sitting on one of those seams would feel those changes. Over billions of years, its radio glow would record that history, like tree rings shaped by seasons of wind and calm. The merger idea also speaks to why the Boötes Void is so large in the first place. If you ask for one giant empty region to arise by chance from the random noise of the early universe, the odds come out very low. Ask instead for several medium-sized voids to form and later combine, and the odds improve. It is still rare, but less extreme. In a universe that has had many billions of years to evolve, rare things can occur in a few places without breaking the rules. As cosmic expansion continues and dark energy grows more important, theory predicts that void mergers become more common. Dense clusters grow denser, but the space between them stretches faster. The thin places thin out further and link up. In that sense, the Boötes Void could be a preview of what many regions will become far in the future: broad, calm basins with only a few long threads of galaxies running through them. The cold spot in the CMB fits into this larger picture. A merged void has a complex profile. Its center may be very underdense, its edges may be sharp where walls meet, and its interior can hold leftover strands. As the whole structure evolves, the gravitational potential along a photon's path does not change in a simple, single-step way. Those details can temper the size of the ISW signal compared with simple models. If some gas at the seams is warm-heated by mild shocks or bursts from small black holes at galaxy centers, it can also reduce the net cooling we measure in the CMB by giving a bit of energy back to passing photons. Both effects help explain why the observed cold patch is real, yet milder than first estimates. The orientation matters too. If we see the void almost face on, then the path length through the emptiest core is long, but so is the path through any boundary gas. Small differences in angle and depth can change how much of each zone a CMB photon crosses. By combining temperature maps with galaxy surveys, astronomers can solve for that geometry more tightly, where the deepest emptiness lies, where the seams run, and how sharply the walls rise. These measurements feed into the broader task of measuring the universe itself. The strength and scale of the ISW effect in directions like Boötes help fine-tune the amount and behavior of dark energy. The layout of galaxies and their motions across the void's face test how dark matter is distributed. Because dark matter sets the scaffolding, the visible structures hang on. Even small anisotropies, tiny directional differences in how light is bent by the walls, can reveal whether the mass there is smooth or clumpy. None of this requires new forces by default. Gravity plus expansion does a lot, but the Boötes field is where we can look for departures if they exist. If dark energy varies slightly from place to place, a large, clean void is a natural arena to notice it. If early universe physics left behind special patches, regions that froze into a different state during a phase change, then merged voids would be where those signatures remain easiest to spot. The low-density interior reduces the noise from ordinary matter and gives subtle effects more room to show. The CMB cold spot, the sparse interior strands, the crowded walls, the mild lensing and radio hints, and the small differences in galaxy chemistry point toward a common story. A set of young voids formed from ordinary early ripples. Dark matter stayed thin there. Expansion favored evacuation, and over time the empty regions grew, touched, and merged. The Boötes Void is one of the clearest examples we have of that growth, large enough and simple enough to trace in multiple, independent ways through ancient light, through galaxy maps, and through the motions and makeup of the few systems that still shine along its seams. The Boötes Void functions like a natural lab, where dark energy stands out more clearly than almost anywhere else. Dark energy is the name for the something that makes space expand faster over time. It seems to fill all of space and makes up about 2/3 of the universe. Yet we do not detect it directly, and we do not know why it exists. In normal regions crowded with galaxies and dark matter, Its effect is easy to hide under stronger local pulls. Inside a deep void, those pulls are weak. The background push has fewer obstacles, so its fingerprints are easier to read. Measurements show that space inside the void expands a bit faster than the cosmic average. In simple language, where matter is scarce, the stretch of space meets less resistance. Some ideas go further. They suggest dark energy might not be exactly the same everywhere or every when. In quintessence models, dark energy acts like a field that can vary with time and with environment, gently strengthening in places where matter is thin. A clean underdense region gives that kind of theory a fair test because the usual masking by gas, stars, and halos is minimal. Another key property is the equation of state, which tells how the pressure of dark energy relates to its energy density. If the equation of state equals 1, dark energy behaves like a true constant energy of empty space. If it differs from 1, the strength can change. Watching how the Boötes Void grows and how fast its boundary moves helps narrow this value. The method is direct. Track the pattern of galaxy motions near the edge, compare it with models, and see which versions of dark energy fit the data best. Signals from ancient light support the idea that the void lets dark energy speak up. The cold spot in the direction of Boötes on the cosmic microwave background, the faint afterglow from when the universe was only a few 100,000 years old, matches what you expect when photons cross a region whose gravity weakens over time. As the void continues to empty, light pays a tiny energy toll, exits a bit redder, and leaves a cooler mark on the sky. That mark builds slowly over billions of years. The pattern hints at a feedback loop. The emptier the region becomes, the easier it is for the general expansion to change the local gravity. The more the gravity changes, the stronger the imprint on passing light. The same setting touches a bigger puzzle sometimes called the cosmic coincidence problem. Why does dark energy become important right around now in cosmic history? If the effect depends in part on environment, stronger influence where matter is already thin, then large voids could become the first places where the push is obvious, while denser zones lag behind. That does not solve the whole puzzle, but it offers a natural way to reduce how finely tuned the present era needs to be. Planned surveys lean on this idea. Space telescopes and wide-field maps will use the Boötes Void as a target to watch. By measuring tiny changes in the positions and speeds of galaxies near the walls over time, peculiar velocities, meaning motion beyond the general expansion, astronomers can trace how the boundary breathes. Pair that with careful lensing measurements, which reveal how mass bends background light, and with updated CMB maps, and you get a three-way cross-check on dark energy's behavior. If dark energy truly varies, the void is where that variation should be most visible. There is also a possible link to the very first moments. Some models argue that today's dark energy could be a faint echo of the inflaton, the field that drove the universe's early burst of inflation. If that is so, then a large, clean void might preserve tiny signatures from that epoch, because there is less later activity to erase them. Subtle alignments in the few internal filaments, or small twists in polarization patterns of background light across the void's face, are examples of the kinds of clues people look for. At the physical edge of the Boötes Void, the flow of matter shows a simple rule in action. Gravity gathers where matter is thick, and matter leaves where it is thin. The boundary is where that contrast is steepest, so the flow points away from the interior and toward the walls. This can look like gravity in reverse, but it is just gravity doing the same job in a different landscape. In general relativity, there is a result related to Birkhoff's theorem that guides intuition. Inside a perfectly empty symmetric shell, the net gravitational pull from the shell itself cancels. In a very underdense domain surrounded by denser structures, the inside feels relatively less pull than the outside, so the motion tilts outward. Surveys of galaxy motions near the wall line up with this view. Close to the boundary, many systems move away from the void faster than the global expansion alone would explain. The speeds rise as you get nearer to the emptiest interior, then ease once you move into the crowded filaments. Simulations that drop test galaxies into a deep underdensity find the same pattern. Orbits toward the center are not stable. The galaxies drift outward and join the walls, while the core remains spare. This helps explain why the few galaxies inside the void look the way they do. They are survivors that formed early, before the underdensity grew strong. Afterward, they were left with little new gas to feed on. Without many neighbors to merge with, without many tides to stir their disks, and without steady inflows of fresh material, they built stars slowly and stayed small. As the push from the evolving landscape continued, they kept their distance from the walls, but did not sink deeper in. Dark matter follows similar logic. We cannot see it directly, but it answers to gravity just the same. If the net flow leans outward, dark matter halos thin in the interior. That removes the main scaffolding that helps normal gas cool and clump. The result is a wide zone whose ability to form new galaxies is suppressed even beyond the edge. Observers describe this as a shadow around the void where galaxy formation lags, extending tens of millions of light years past the nominal boundary. Gas temperatures add another thread. If gas fell straight onto a dense wall under normal gravity, it would heat as it compresses. In the Boötes field, some measurements find cooler than expected gas near the edges. That can happen if the inflow is weaker, more sideways than straight in, or if the energy picked up during the fall is spread over a broad, slowly changing region. In the language of work and energy, the field is not doing as much positive work on the gas as a steep, compact well would. The outcome is a gentler interface, a wide, cool sheet, rather than a sharp, hot shock. High-energy particles, like cosmic rays, also tell part of the story. Their paths bend in gravitational fields. Through a large, shallow underdensity, the bending can steer particles away from the line of sight, leaving a faint deficit, a shadow over a wide patch of sky. That shadow aligns with other signs that the interior has less mass than average and that the boundary is where most of the action lives. These behaviors are consistent with standard gravity, plus an evolving, underdense landscape, but they also open a door to tests of alternative ideas. Some theories modify gravity's law on very large scales or in very low-density regimes. Others let dark energy interact weakly with matter, changing how structures grow. A clean void is a good stress test for such proposals, because small deviations are easier to spot when ordinary matter is scarce. If the relation between mass and motion in the Boötes field fails to match general relativity's predictions, or if lensing maps disagree with dynamics in a patterned way, that tension would point toward new physics. The observational program is straightforward, even if the measurements are hard. Map the wall in detail. Watch the tiny drift of its galaxies. Measure how background galaxies are lensed as their light crosses the boundary. Read the temperature and polarization of the CMB across the void's face, and compare all of it with simulations that include both ordinary ingredients and proposed changes. Consistency across these methods counts more than any one line of evidence on its own. Taken together, the picture is one of a broad, low-density basin where the general expansion asserts itself, where matter flows to the sides rather than toward the center, and where a handful of early-made systems remain, faint and far apart. The interior's quiet, makes dark energy easier to measure, whether it is truly constant or only nearly so. The boundary's contrast makes motion easier to track and test. If a new behavior of gravity or a subtle change in dark energy exists, a large, clean void like Boötes is one of the places most likely to reveal it. The gravitational desert does not stop neatly at the drawn edge on a map. Its influence bleeds outward, shaping how gas cools, how stars light up, how halos gather, and how background signals bend. That reach is exactly why voids are valuable to study. They press on the rules that build the cosmic web and make it possible to see where those rules hold and where they might need to bend. The cosmic web is the great framework of the universe, a three-dimensional network made mostly of dark matter. Filaments span vast distances, metered clusters, and guide gas into galaxies. Between these strands lie broad basins with less matter voids. In a well-connected web, filaments thread even the empty places, crossing and linking distant regions. The Boötes Void breaks that pattern. It is a wide patch where the web's expected bridges are missing or faint, a gap that leaves nearby strands hanging without partners to join. The image is simple: a spider web with a section torn away, the silk thinning to loose ends around an open hole. When scientists build computer models that start just after the Big Bang and let gravity pull on dark matter and gas, a web appears on its own. Voids form naturally, and some become large. Yet models that use standard ingredients, cold dark matter plus general relativity, struggle to make a void as big and clean as Boötes. Even with extreme starting ripples, the simulations tend to leave small threads through the emptiness, or fill the interior with more halos than we observe. This mismatch hints that something about the initial conditions, the growth of structure, or our assumptions about dark matter may be incomplete. The break in the web does not stop at the empty core. It affects the region around it for hundreds of millions of light years. Filaments that should cross the area and tie into structures on the far side end abruptly at the boundary. The result is a set of isolated clusters and groups that look like orphaned islands. In these neighborhoods, the usual support for building new galaxies is thin. When the scaffolding is missing, gas has a harder time cooling and condensing, so the rate of galaxy formation drops. The effect spreads outward like a soft shadow from the central hole, marking a broad zone of lower activity. Flows of matter also change. In a healthy web, material slides along filaments toward the nodes where clusters live. Around the Boötes Void, those streams bend and pool at the edge instead of crossing the interior. The picture looks like water skirting a sinkhole in a dry lakebed. The currents curve, the traffic shifts to the sides, and the middle stays bare. Over billions of years, this redirection builds the dense walls around the void while starving the interior, keeping the gap sharp. Clues that the web faltered here go back to early times. The cosmic microwave background, the faint glow left from when the universe was young, carries patterns that trace the first tiny lumps and dips in density. In the direction of Boötes, the signal suggests fewer of the small seeds that would have built filaments later on. It is as if the blueprint for a bridge was faint or missing from the start, so the later structure never formed cleanly. Some researchers describe the region as a possible boundary between patches of space that expanded a little differently during inflation, the very early growth spurt. If two patches grew with slightly different rules, the seam between them could be hard for the web to cross. In connected regions, gravity's influence moves along filaments, keeping far-flung pieces of the web in communication. A large, clean void interrupts that link. The space on one side cannot tug as efficiently on the other, so the whole network's timing shifts. When scientists analyze the topology, the shape, and connectivity across scales from single galaxies up to superclusters, they find that the Boötes region changes the pattern over nearly 1 billion light-years. It is the largest known disturbance of the web's usual layout, not a local wrinkle, but a continental-sized gap. All of this forces a hard look at dark matter, the unseen mass that makes up most of the web. Dark matter interacts mainly through gravity, so we trace it by its effects: how it bends light, how it speeds up galaxy motions, how it shapes the web. In standard pictures, even voids hold a fair share of dark matter, just less than average. But lensing studies careful measurements of how background galaxies are subtly distorted show that the Boötes region holds far less dark matter than expected, perhaps under 10% of the cosmic mean. That is one of the deepest deficits measured. If the scaffolding is that thin, it explains why the interior forms so few galaxies, yet it also raises a new puzzle. The handful of galaxies inside look, in many ways, like ordinary small systems. Their stars and chemical fingerprints can be explained by normal growth paths. How did they form without the dark matter support that usually anchors a galaxy? One answer is that they formed early, before the region emptied so fully, and then survived as the environment drained. Another possibility is that the kind of dark matter in this patch behaves differently from the cold, slow particles used in most models. Warm or hot dark matter, which moves faster, tends to wash out small clumps and could leave a smoother interior. A different idea lets dark matter interact weakly with itself. Over long times, such interactions might thin the remaining halos even more in an already underdense place. Rotation curves the way a galaxy's stars and gas orbit as you move outward provide another probe. In many galaxies, the outer parts spin faster than visible matter alone can explain, evidence for dark matter halos. Some of the Boötes galaxies show flatter or lower rotation speeds than similar galaxies elsewhere, hinting that their halos are lighter. That supports the broader picture of a region poor in dark matter as well as in stars. If the standard mix of dark matter and gravity still struggles to fit all the signs, voids like Boötes become testing grounds for modified gravity. The idea is not to throw out general relativity, which works extremely well, but to ask whether its large-scale behavior in very low-density settings has small corrections. The attraction of such models is that they might explain both the thin interior and the sharp response at the edge with a single change in the force law. The cost is high. Any new rule must also match the many areas where standard gravity already succeeds. Voids offer a clean place to look for mismatches, because there is less normal matter to confuse the signal. The web's missing bridges do not stop matter from moving altogether. Instead, the region is ringed by coherent streams, long chains of galaxies, and dark matter that trace smooth paths around the void. Surveys show that the largest of these flows is the Perseus-Pisces chain. It arcs along the void's northern rim, thousands of galaxies moving in roughly the same direction. The coherence holds over hundreds of millions of light years. Imagine a slow river turning around a bay. The water keeps its course, curving gently, yet staying organized, far downstream. In simulations, once flows like these settle, they last. They carry galaxies away from the interior and toward the denser nodes, feeding the walls and clusters that grow there. Where multiple streams meet, matter piles up, and those crossroads become the brightest, busiest parts of the boundary. These are the places where we see big walls and knots, cosmic deltas where river-like currents deposit their load of gas and stars. Motion measurements back up the picture. Galaxies in the streams have extra speed on top of the general expansion, directed along their paths. The numbers reach into the hundreds of kilometers per second, among the largest coherent motions seen on such scales. The direction and size of these peculiar velocities match what gravity predicts for a large underdensity. The flows bend around the hollow and settle into the denser country beyond it. Travel through a medium also changes a traveler. Galaxies that ride these currents feel gentle pressure from the thin gas between galaxies. The pressure can strip some of their outer gas, which in turn slows future star formation. Close passes are more likely where streams converge, so tides, differences in pull across a galaxy, can tug out tails or trigger short bursts of new stars. Many stream galaxies show signs of these quiet encounters written in faint plumes and lopsided disks. The streams leave marks on ancient light as well. The cosmic microwave background, viewed with high precision, shows tiny Doppler shifts in directions that line up with major flows. That means parts of the web were already in motion in an organized way when the universe was young, and the Boötes region sits at a key bend in those currents. The signal is small, but consistent with a long-lived pattern. The void's reach extends even beyond what we map as its edge. Over a span of more than 1 billion light-years, the directions of flow, the rates of star birth, and the shapes of faint filaments show the hollow's influence. Some streams appear to have been steered more than once as the void grew. Their paths curve in ways that record the history of the changing gravitational landscape, first a gentle detour, then a stronger bend as the interior thinned further and the boundary walls rose. These currents also reveal where dark matter still hides, because the flows respond to total mass, not just the visible part. By comparing the observed paths and speeds with models, astronomers can map the three-dimensional mass field, where the invisible ridges lie, how thick the walls are, and where the seams run inside the broad emptiness. The maps show that dark matter follows the same general pattern as normal matter around the void, but with small differences, smoother strands, broader bends that reflect its tendency to spread and resist clumping when the background density is low. Across the larger sky, similar streams connect to other superclusters and basins. The Boötes region is not an isolated oddity. It is a major junction in a global network of motion. Galaxies, gas, and dark matter flow along these highways from one large-scale structure to another, guided by the combined pull of dense knots and the gentle push of expanding, underdense basins. The network suggests a future in which the richest clusters keep drawing in material along a few favored routes, while the spaces between them open wider and link up into even larger voids. Circling back to the web itself, the Boötes gap has forced new questions about how connected the universe must be. If a hole this large can open and stay open, what sets the limits on the web's continuity? How often can filaments be cut or rerouted by evolving basins? Can extreme underdensities erase smaller bridges so completely that two sides stop exchanging matter for the rest of cosmic time? The answers matter because they shape not just where galaxies live, but how information, gravity, light, and even the paths of high-energy particles travels across the map. One way forward is to keep combining lines of evidence. Lensing shows the total mass. Galaxy counts trace the bright structures. Peculiar velocities reveal the motion. The CMB adds the oldest stage lighting and the way it changes as light crosses evolving structures. When all four methods point to the same shape and behavior, confidence grows. When they differ, the gaps show where models need repair. Another path is to refine the physics of the dark sector. If dark matter has a small interaction with itself, that would change how halos survive in strong voids. If dark energy varies slightly with environment, that would tilt the balance between thinning interiors and thickening walls. Both ideas can be tested in places like Boötes. where the signals are not drowned out by crowded scenes. Subtle differences in how light bends at the edge compared with how galaxies move could distinguish between a change in gravity and a change in the mix of dark components. What the Boötes Void ultimately shows is that the universe's largest patterns are both robust and sensitive. Gravity and expansion build webs and basins almost no matter what, but details matter. The depth of a hollow, the thinness of a strand, the timing of flows, and the mix of unseen matter and energy can add up to a region that departs strongly from average. The Boötes Gap is one such region. It exposes the limits of simple expectations, pushes models to grow, and provides a clean stage on which to watch the rules of structure formation at work when the usual crowd is gone. As maps sharpen, more faint galaxies may appear in places that now look blank, and the filaments inside may show branches we cannot yet trace. Even then, the main character, the broad, quiet basin, will remain. It shapes the courses of rivers of matter, trims the bridges of the cosmic web, and sets a wide arena where we can test how dark matter and dark energy share the job of building and unbuilding the universe's largest forms. The Boötes Void offers a quiet look at a far future in which space has stretched so much that every galaxy stands alone. In the standard picture, dark energy keeps the expansion of the universe accelerating. Over the next tens of billions of years, galaxies beyond our small gravitational neighborhood drift out of view as their light redshifts pass detectability. Local islands remain bound. Distant shores slip beyond any horizon we can observe. Inside the Boötes Void, that future is already sketched in. The separation between its few galaxies is so large that, for any observers living there, the night sky would hold little more than their own stars and a thin background glow. The galaxies that endure inside the void reflect this isolation. Cut off from steady supplies of fresh gas, they form stars slowly and then barely at all. Their light is rich in older, redder stars, with fewer blue, short-lived ones. Astronomers sometimes call such systems quenched, meaning their star-making factories have mostly shut down. The reason is simple physics. Without nearby companions to stir gas and trigger collapse, and without filaments to feed them, the conditions for new stars are rare. Over long times, the result is a population that looks aged ahead of schedule. If the current expansion continues and dark energy keeps its pressure-like behavior, models that extend far beyond present ages predict a universe that, after trillions of years, resembles the void everywhere. The average distance between bright systems grows. The links between clusters thin. The web that once tied the cosmos together becomes sparse. What is now a rare environment would become the norm. Gravitationally bound groups like the Milky Way and Andromeda, which are expected to merge, would remain as single, long-lived islands. But wide oceans of space would separate those islands. A sky this spare changes how knowledge can grow. In a galaxy deep inside a strong void, a young science would have fewer external signposts. With almost no bright neighbors, there is little direct evidence for a universe beyond the home system. The idea of expansion is harder to infer without a ladder of galaxies at different distances. Even so, one ancient clue remains: the cosmic microwave background, the faint radio microwave afterglow from the early universe. The CMB would still be detectable, though redder and dimmer as time advances. Without nearby galaxies for scale, its meaning would be difficult to decode. The signal would look like a near-uniform hiss across the sky, a puzzle without an obvious key. As the void continues to thin, even its few survivor galaxies will slip out of one another's view. Each system becomes truly alone. the temperature of sparse intergalactic gas drops toward the universal floor set by the expansion. With little matter to compress and heat, there is less energy exchange. The region approaches a thermal state that foreshadows a general heat death, where useful differences in temperature and density have declined. In the language of thermodynamics, entropy, the measure of how spread out and even things are, rises as structure empties. A deep void is not perfectly uniform, but it heads in that direction faster than denser neighborhoods do. Speculative physics pushes even further ahead. Some theories allow for proton decay on timescales so long they dwarf stellar ages. If such decay happens, it would gradually dissolve ordinary matter everywhere. Whether isolation inside a void would delay any local consequences is uncertain and model-dependent. The idea appears because interactions that require dense environments happen less often where there is almost nothing to interact with. Still, these are distant possibilities, far beyond the time when stars fade. What the void provides now is a setting to test the rules that shape that long arc. The Boötes Void also acts as a measuring tool. Most ways to track the universe's expansion rely on bright objects, supernovae, variable stars, galaxy clustering. A deep underdense region adds a different approach. Measure expansion through emptiness itself. By mapping the void's boundary carefully, and by tracking the peculiar velocities of galaxies near that boundary motion, on top of the general expansion, astronomers can infer how fast the interior grows. Analyses suggest that the void's effective expansion outpaces the cosmic average by on the order of 10%. The difference is small in any one snapshot, but becomes clear over long baselines. There is a second handle in the sky. The angular size of the void, the patch of sky it covers, combined with distance estimates to edge galaxies, lets observers reconstruct how large the empty region was at earlier times. Light from those galaxies left long ago, so each measurement is a look back to a different stage. Put many such measurements together and a growth curve appears. In a dense zone, local motions and interactions complicate the picture. In the Boötes field, the simplicity of the interior means fewer confounding effects. That is why cosmologists call it a clean laboratory. Redshift adds a third thread. In standard expansion, a galaxy's redshift is tied to distance and the overall stretch of space. In a strong void, light picks up an extra stretch as it crosses an evolving gravitational landscape. For the void's few galaxies, their observed redshifts tend to be slightly higher than you would expect from distance alone. The offset is small, but consistent with faster local expansion in an underdense patch. This provides direct observational evidence that environment matters. The same global universe can expand differently in thin and thick places, in ways that general relativity and large-scale flow models predict. These measurements help with a well-known tension in cosmology. Different methods yield slightly different values for the present-day expansion rate for the Hubble constant. Techniques that use nearby distance ladders and techniques that use early universe physics do not always agree. Part of the gap could come from how environment biases specific measurements. If underdense corridors are common along some sight lines used for standard candles, and if those corridors expand a bit faster, then distance and redshift can be mismatched in a patterned way. Studying a prominent void where the effect is largest helps calibrate those biases. It does not solve the entire tension by itself, but it sharpens which parts of the discrepancy belong to method and which might point to new physics. The cold imprint in the CMB contributes independent limits. The integrated Sachs-Wolf effect, the energy lost or gained by photons that cross changing gravitational wells and basins, depends on how expansion has evolved. The size and depth of the Boötes cold feature, mild as it is, restrict how fast the void can have grown. It also checks models in which dark energy varies with environment. If dark energy's pressure-like behavior strengthens in thin regions, the ISW signature should reflect that. Compared with simple predictions, the observed depression is smaller than a naive one-void model would give, which pushes theory toward merger histories, edge heating, and other details that temper the signal. Expansion inside the void also nudges distance measures for background objects seen through or near its face. Standard candles and standard rulers, events and patterns with known luminosities or sizes depend on accurate maps of how space stretches along the line of sight. If a path runs through a wide, faster expanding basin, the light can arrive a bit redder and later than a flat average would predict. Correcting for this requires models that include how expansion varies with local density. Those corrections then feed back into improved estimates of supernova distances and galaxy clustering scales in this part of the sky. To match the void's expansion and lensing signatures at the same time, computer models need specific mixes of matter and dark energy. If the matter density is too high, the void cannot stay as empty as observed. If too low, the walls would not be as sharp. If dark energy behaves exactly like a constant everywhere, the growth curve must still bend in the right way to fit both the cold imprint and the current boundary motion. Some exotic alternatives are trimmed by these joint constraints. Others, like gentle, environment-dependent dark energy or very weak dark matter self-interactions that change halo survival in thin regions, remain eligible and testable. The void is not a single number. It has an interior with parts that evolve at slightly different speeds. Near the center, where density is lowest, the effective expansion can be a bit higher than near the edge, where the walls tug back more strongly. By comparing redshift, lensing, and peculiar velocity maps across different chords through the void, astronomers build a three-dimensional profile of these differential rates. The profile records formation history, which zones emptied first, which seams mark old mergers, where hidden strands still carry a few galaxies. Statistics tie the story together. Each probe lensing, galaxy counts, velocity flows, CMB features carries uncertainties and potential biases. Combined in the same region, they act like cross-checks. A model that fits the lensing but misses the velocities is incomplete. One that fits both but fails, the CMB, fails the timing. In the Boötes field, the joint fit reduces error bars on key cosmic parameters. Even small gains matter when the goal is to distinguish between a dark energy that is truly constant and one that is only nearly so. The measurement program also refines a practical tool, using voids as complementary rulers. A population of well-mapped voids, spanning different sizes and redshifts, can act as a set of gauges for how expansion and structure growth track each other. The Boötes Void, being large, simple, and nearby enough for detail, anchors the bright end of that set. Smaller voids add statistics. Boötes adds leverage on extremes. With sharper maps and longer baselines, the method can reach finer questions. Does the relation between local density and expansion rate curve in the same way at the deepest emptiness as it does in moderate basins? Do the walls grow at the same pace in all directions? Or are there preferred paths where flows are stronger? Are the few internal galaxies moving along a persistent filament that runs through the whole void? Or are their paths better explained as tracks along a seam left by merged basins? Each answer tightens how we model large-scale evolution and how we extract cosmic parameters from data. The Boötes setting also teaches caution. When an empty foreground sits between us and a distant test object, it can bias more than one measurement at once: brightness, apparent size, timing, and even color if dust or very thin gas contributes. The void's clean interior reduces some complications, but not all. That is why multiple, independent lines of evidence are valuable. Where they agree, confidence grows. Where they diverge, they point to hidden systematics or to physics not yet captured in the models. Against this technical background, the long view remains simple. A deep void demonstrates how the universe evolves when gravity has little to pull on and dark energy has room to act. The result is separation, cooling, and quiet. The few survivors age in place. The boundary gathers matter that would otherwise cross, building bright walls and busy junctions. The inside becomes a stable basin in the flow of the cosmic web. If the universe's acceleration continues, more regions will drift toward this state, and the map will look more like the Boötes field writ large. The scientific value is twofold. First, the void provides a clean testbed, fewer moving parts, clearer signals, and controlled ways to compare theory and observation. Second, it offers an early example of a fate that models predict on longer timescales: isolation growing, structures thinning, and the lights of the universe spaced farther apart. Whether the Boötes Void is a straightforward preview of that future, or a sign that the dark sector holds surprises, is exactly what ongoing measurements aim to decide. Deep in the Boötes Void, the newest telescopes are finding faint signs that empty does not mean simple. The void was first mapped by its lack of bright galaxies. With far more sensitive instruments, that darkness now shows thin threads of matter and tiny systems so dim they nearly blend into the background. Ultra-deep images from space and from large ground observatories reveal objects at the edge of visibility, dwarf galaxies with so few stars that some hold less light than a single rich star cluster. In a few, the average distance between one star and the next approaches the gap between neighboring star systems in our own galaxy. These are borderline cases, right on the line between a bound galaxy and a loose association that may drift apart over time. Radio observatories add a different clue. Inside the void, they pick up very weak, spread-out radio glow that does not match the usual fingerprints of star-forming regions or active black holes. Rather than coming from compact points, the signal rises from broad patches. One idea is that the radio comes from thin, warm plasma-ionized gas moving through weak magnetic fields stretched across the emptiness. Another is that we are seeing hints of matter in unusual states that survive only where the density is extremely low. These are working ideas, not conclusions, but the void provides the rare conditions to test them. Infrared maps show something else. Faint dust warmed just enough to glow beyond visible light. The dust appears in wisps and filaments that run for millions of light years. Dust is made of tiny grains, carbon, silicates, and ices built in old stars and spread by stellar winds and supernovae. Finding it in such a sparse region means some material flows through the void on long paths, and some energy source keeps the grains slightly warm. The arrangement into filaments hints that even in near emptiness, gravity and motion can draw material into simple, large-scale patterns. Searches for gravitational waves, ripples in space-time, are turning their ears toward the void as well. No confirmed signals have been traced to the Boötes region yet, but theory leaves room for rare objects that could be easier to preserve in quiet space. Ancient black holes formed in the early universe, or topological defects like strings that some models predict. If such relics exist, the void's isolation reduces the chance that later events would hide or destroy their signatures. X-ray observatories find a surprise of a different kind. Extremely hot, very thin gas spread through parts of the interior. the temperatures are far above the usual intergalactic medium. There are few obvious engines nearby, no bright clusters, few massive galaxies, so the heating must come from gentle but widespread processes. Weak shocks from large-scale flows, turbulence in rarefied plasma, or long-lived input from the handful of faint, active nuclei along the seams. The gas is too thin to shine brightly, which is why it took deep, patient exposures to reveal it. Because the void reduces foreground clutter, it is becoming a target for dark matter searches. Dark matter does not shine, but its gravity shapes orbits and bends light. Some models allow dark matter to have faint self-interactions, forces that act between dark matter particles themselves. In crowded regions, those subtle effects are buried under ordinary signals. In a near-empty field, a small, unusual pattern in how mass is arranged, or a tiny departure in how particles scatter, could stand out. If any such hints exist, the void is one of the best places to look. Neutrino telescopes add to the watch. Neutrinos interact only very weakly with normal matter, but if there is a hidden dark sector with its own particles and forces, neutrinos might respond to them in special ways. A persistent excess of neutrinos from the direction of a large void would be a clue that something beyond the standard model of particle physics is at work. So far, results are consistent with noise, but the limits grow tighter with time. High-energy cosmic rays, charged particles moving near light speed, arrive at Earth from all directions. Their paths bend in magnetic fields, and gravity can steer them as well. When researchers map the slight unevenness in their arrival directions, they find patterns that could tie to the Boötes region. Some paths may be nudged by invisible concentrations of mass along the void's edge. Others may be deflected away from the emptiest core. These hints are small and need careful checks, yet they fit what we expect when the large-scale landscape pushes flows to the sides. The cosmic microwave background, CMB, the afterglow of the young universe, is sensitive enough now that secondary effects from the void become measurable. Hot electrons can give passing CMB photons a tiny energy boost, an effect called inverse Compton scattering, part of the Sunyaev-Zeldovich family of signals. Compact masses can weakly lens the background, slightly blurring or shearing its grainy pattern. In a deep void, both changes are faint. With long observations and clever statistical tools, maps begin to show them. Matching these subtle signatures to the visible matter helps complete the mass map and tests how much unseen structure still threads the interior. Computer models that try to reproduce the void's interior predict material we have not yet seen directly. Some halos may have failed to form many stars, so-called dark galaxies. There could be a population of isolated brown dwarfs, objects too small to sustain normal starlight. More speculative ideas include dark stars, theoretical bodies powered not by nuclear fusion, but by the energy released if dark matter particles annihilate in their cores. These ideas stretch current data, but they offer targets for future searches with deeper sensitivity. Hunting for such faint material pushes instruments to their limits. Telescopes must stare for hundreds of hours at one patch. Detectors must reduce noise to levels once thought unreachable. Data pipelines must sort real signals from artifacts left by the atmosphere, the instrument, or the sky. That effort does more than probe a single region. It drives technology forward, which then benefits many other fields in astronomy. The discovery of the Boötes Void also changed how astronomers look at the rest of the universe. Once one very large empty region was mapped, surveys began to search systematically for others. The result is a catalogue of hundreds of voids of many sizes and shapes. They form a hierarchy. Modest basins a few tens of millions of light years across, mid-size voids like familiar local examples, and rare giants, often called supervoids, that approach the scale of the largest patterns we see. Together, they show that emptiness is not an odd exception. It is a standard part of the cosmic design. Among these, a vast, low-density region in the constellation Eridanus stands out for its size, stretching close to the 2 billion light-year mark in some analyses. Whether a single supervoid or an overlapping chain of several, it has even fewer bright galaxies per volume than most voids. Light would take on the order of billions of years to cross it. Its existence reminds us that the universe organizes both matter and emptiness across staggering scales. Each void carries its own story. In the Sculptor region, deep imaging points to a recent trickle of new small galaxies inside the basin, suggesting that some voids can slowly refill along weak internal filaments. The Capricornus area shows an excess of dwarf galaxies compared with similar voids, hinting that under the right conditions, small halos can gather gas and light up, even when large ones do not. Differences like these help separate which parts of void evolution are universal and which depend on the neighborhood. When researchers measure many voids together, patterns appear. Larger voids tend to be emptier, more spherical, and to expand their boundaries slightly faster than smaller voids do. Those scaling relations provide tests for models of structure formation. A theory that predicts too many lumpy, slow-growing basins fails when compared with the clean shapes we see. One that erases internal features too quickly cannot match the faint strands found inside some voids. Voids do not lie at random across the sky. They too form networks. Between the dense filaments of the cosmic web, there is a negative space network of lower than average density, connected by tendrils that are simply less crowded. Maps that trace where galaxies thin out show that voids often touch and even overlap, separated by walls that may be only a few tens of millions of light years thick. The Boötes region sits inside this larger pattern, with its giant basin surrounded by smaller basins that line up along preferred directions. Environment matters. Voids born in already sparse neighborhoods have more room to grow and can reach sizes like Boötes. Voids that form next to massive superclusters face stronger tugs from outside and tend to stay smaller and less empty. This dependence helps explain why catalogs show a wide range of sizes and shapes, and why some voids look almost round, while others stretch in one or two directions. The CMB offers a broad, independent check on this network. Many large voids imprint small cold spots through the integrated Sachs-Wolf effect, the same energy toll that makes the Boötes direction appear cooler. When the sky is filtered to highlight features on the right angular scales, a pattern of mild, cool patches emerges that lines up with known voids. None is as prominent as Boötes, but together they trace the negative space of the cosmic web and help measure how the universe's expansion rate has changed. Simulations that include realistic void populations match large-scale observations better than those that modeled only the bright structures. When both sides of the pattern, dense and thin, are present, the flows of matter, the growth of clusters, and the balance of star formation across environments line up more closely with surveys. In other words, voids are not leftover gaps. They are active parts of the machinery that shapes the cosmos. Some voids show behaviors that stretch current models. A handful display hints of slow internal rotation, measured as tiny, coherent twists in galaxy motions across their faces. A few appear to hold pockets with more dark matter than their light would suggest, perhaps because of unseen internal strands or projection effects along the line of sight. Nested voids, small basins inside larger ones, also appear in deep maps, suggesting that emptiness builds on multiple scales at once, much as dense structures do. These puzzles are valuable. If a void spins, even slowly, what started that rotation? If a basin holds an odd concentration of mass, is that a hidden filament or a sign of different physics? Are nested voids simply the natural outcome of the same growth rules applied in stages, or do they point to changes in the early seeds laid down before galaxies formed? Each case adds a constraint that models must meet. The family of known voids keeps growing with survey depth and sky coverage. New instruments will push to higher redshift, greater distances and earlier times, so astronomers can watch how void properties change across cosmic history. The aim is clear: measure their sizes, shapes, and internal features as a function of age, follow how their walls gather matter, and compare those curves with predictions for different mixes of matter and dark energy. Back inside Boötes, the search for hidden matter continues. Ultra-faint dwarfs are checked for motion that shows they are truly bound. Radio maps are refined to separate low-level plasma glow from background noise. X-ray images are stacked to improve sensitivity to thin hot gas. Lensing reconstructions are sharpened as deeper catalogs of background galaxies add more sightlines through the basin. Neutrino and cosmic ray monitors integrate over long times, looking for small, steady excesses from the void's direction. Each effort draws a more detailed picture of a region that began as a blank and is now a delicate sketch. In that sketch, the same themes repeat. Where matter is scarce, small differences in expansion and gravity stand out. Weak flows can shape long structures. Rare objects that might be erased in busy places can persist. Clean basins like Boötes are where these effects are easiest to see. They test how the dark components of the universe behave when the usual bright crowd is gone. They reveal how the negative space of the cosmic web guides the positive space we tend to watch. And as catalogs extend to earlier times, they set a timeline for how emptiness itself grows one more curve to place next to the better-known histories of clusters, galaxies, and stars, so that models of the whole universe can be judged not only by what shines, but by what does not. Comparing many voids side by side turns emptiness into a measuring tool. A single example can be striking, but a family of voids gives statistics the kind of weight needed to tell which theories of structure growth match nature and which do not. The idea reaches back to the first instant of history we can model: cosmic inflation. In that brief phase, space is thought to have expanded at an almost unimaginable rate, when the universe was far younger than a fraction of a second. Tiny quantum jitters in the vacuum, random ups and downs in energy were stretched to cosmic size. Those ripples became the seeds that later grew into clusters, filaments, and also the broad basins we call voids. If that story is right, the biggest, cleanest voids are fossils from that time. Different versions of inflation make different predictions about how strong those first ripples were on each scale. Some paint a very smooth spectrum of fluctuations. Others add small bends or bumps in the pattern. The sizes, shapes, and number of voids at each size can check those ideas. If very large underdensities are common in one model but rare in another, a map of real voids will favor the model that matches. The Boötes Void, because of its scale, sits at the edge of those tests. It either must be a tail event that fits the predicted pattern, or it points to missing physics in our early universe script. The oldest light in the sky, the cosmic microwave background, gives a parallel record. Inflation should leave specific marks in that light: tiny temperature differences, and a delicate polarization pattern tied to how the first ripples moved. In directions where the line of sight crosses a large void, The temperature is cooled a little by the way light loses or gains energy as gravity slowly changes a process, often nicknamed the integrated Sachs-Wolf effect. For the biggest voids, the size and depth of these cold patches should line up with inflation's predictions about the strength of the original ripples on large scales. In practice, the Boötes direction does show a mild cold area that points toward a long-standing underdensity. Its amplitude and angular span set limits on which versions of inflation can still stand. Polarization adds an extra handle. The CMB's polarization is usually described as E modes and B modes, two patterns that differ in shape. Primordial gravitational waves from inflation would leave a faint B mode signal. Massive structures along the way can lens and twist the background's polarization, mixing some E into B. A large, clean void changes the lensing in a gentle, predictable way. By measuring polarization across and around the void and comparing it with sky regions that avoid big structures, observers can look for small boosts or deficits that either reveal or hide the sought-after primordial pattern. The signal is tiny, but the geometry of a well-mapped void helps separate it from noise. Some models of the early universe go beyond a single, smooth inflation field. They allow space to break into domains with slightly different properties, like water freezing into crystals with different orientations. In such pictures, boundaries between domains could be hard places for ordinary structure to cross. On a sky map, those seams might appear as supervoids or as long, underdense corridors. In the most speculative versions, even the values of basic constants could vary across domains by tiny amounts. If anything like that ever happened, a giant underdensity might be one of the few places where a leftover sign could survive. This is a working hypothesis, not a claim, yet it shows why extreme emptiness is scientifically useful. It preserves history that crowded zones erase. Another early universe link comes from how inflation's fuel behaved. Physicists describe the field that drove inflation, the inflaton, by an equation of state, a simple relation between its pressure and energy density. The details set how fast space expanded and how ripples grew. Much later, we measure how voids expand and evolve. If our measurements of void growth, lensing, and CMB imprints prefer one expansion history over another, they quietly favor the corresponding inflation physics too, tying the earliest second to the present map. Quantum field theory adds yet another bridge. During inflation, quantum fluctuations affected not only matter density but also the vacuum energy, the baseline energy of empty space. If small, long wavelength variations in that energy survived, you would expect underdense regions today to show tiny differences in how the push of space behaves. In plain words, there could be a weak link between the old quantum froth and the present-day behavior we call dark energy. Voids like Boötes are where such a link would be easiest to notice, because there is less normal matter to cover it. Statistics of voids test the shape of those first ripples in another way: non-Gaussianity. Gaussian here means the randomness has the simplest, bell-shaped form, with no preference for skewed lumps or long tails. Many inflation models predict a nearly Gaussian pattern. Others predict small departures. The counts, shapes, alignments, and clustering of voids are sensitive to such departures. If voids tend to be more elongated or more isolated than a Gaussian seed would allow, that is a clue. Studies across many surveys show relations bigger voids are rounder and emptier, smaller ones more lumpy, that agree broadly with simple seeds. But extreme cases like Boötes tighten the bounds on how much non-Gaussianity is allowed. A few theorists have even suggested that voids might carry faint traces of quantum entanglement from inflation. Entanglement is a quantum link between systems, where measuring one affects predictions about another. Inflation stretched tiny, entangled patches to vast distances. If any residue of those links survives, it would show up as correlations between far-apart regions that go beyond ordinary cause and effect in later times. This is a delicate, early-stage idea. The way to test it is to cross-correlate void maps with CMB patterns and with other traces across very large scales, looking for matched wiggles that are too strong or too broad to arise from late-time physics alone. Some inflation stories never really end. They allow eternal inflation, where new space keeps sprouting elsewhere, while inflation shuts off inside bubbles. Our visible universe would be one such bubble. If two bubbles interacted long ago, the contact could have left a faint, disc-like bruise in the CMB, or a long underdense swath in today's structure. Supervoids become places to search for such broad features. Observers check for concentric rings in temperature, for slight alignments in polarization, and for edges in galaxy counts that line up across many wavelengths. So far, nothing has been proven, but the method is clear and improving with new data. Future gravitational wave observatories add a fresh angle. Primordial waves from inflation are expected to be extremely weak. Large-scale structure can act as a lens for these waves, much as mass lenses light. In principle, a big, clean void would defocus them slightly, while dense walls would focus them. The effect is tiny, yet with detectors that can watch long baselines and low frequencies, you can imagine mapping how a background of ancient waves is shaped by today's cosmic geography. If that background is found, cross-checking its pattern against well-mapped voids would become a direct test of our earliest physics. Set against these grand links is a hard, grounded fact. Standard growth with standard seeds has trouble producing Boötes. The baseline picture starts with the density differences we see in the CMB when the universe was about 380,000 years old. Gravity then amplifies those differences. Big basins grow, but they are also threaded by thin strands and small halos. When simulations are tuned within observed ranges and run forward, they make large voids, yet they rarely achieve one as broad and clean as Boötes. The odds of making a void this empty by random chance are tiny, often quoted as well below a few parts in millions. That does not prove the picture is wrong, but it does nudge us to look for missing pieces. One set of ideas borrows from condensed matter. The early universe could have experienced phase transitions, changes in state similar in spirit to water freezing, when fields that set particle properties shifted. Pockets that settled differently would create boundaries. At those seams, structure might be suppressed or rerouted, leaving long-lived underdensities. Another idea calls on primordial black holes, very early condensations that later evaporated through Hawking radiation. If many formed in a region and then faded, the energy they dumped into their surroundings could have pushed gas and even dark matter outward, leaving a hollow that later expansion preserved. These are strong claims and need clear observational marks, specific backgrounds of radiation, leftover element patterns, or lensing signatures to move forward. Modified gravity is another path. General relativity has passed every precise test we can do, from solar system scales to binary pulsars to the motion of galaxies. But some theories tweak how gravity behaves across cosmic distances or at very low accelerations. Those tweaks can change how quickly voids grow and how sharp their edges become. The key is consistency. Any theory that makes it easier to carve a supervoid must still match the expansion history, lensing maps, galaxy motions, and the CMB. Voids like Boötes become stress tests because they minimize the clutter from ordinary matter. Dark matter physics can also play a role. In the simplest picture, dark matter is cold and collisionless. It moves slowly and interacts only via gravity. If, instead, dark matter had weak self-interactions early on, it might have been easier to sweep from an underdense patch and harder to rebuild there later. If a fraction of the dark matter were warmer, moving faster, small halos would be washed out, leaving smoother basins. Even a tiny coupling to a dark radiation background in the early universe could tilt the growth of structure in subtle ways that show up first in extreme voids. Chemistry inside void galaxies provides another line of evidence about early conditions. The few systems found in deep basins often have low metallicity, meaning their stars and gas lack heavier elements. That is expected for systems that formed slowly and in isolation. Yet some show odd ratios among certain elements, which could hint at different early enrichment paths, or at slight differences in how the first stars lived and died in underdense settings. Since those first stars also seeded the universe with light elements produced in the Big Bang, patterns in void galaxies can help check whether nucleosynthesis, the making of helium, lithium, and more played out identically everywhere. Large-scale correlations join the dots. When researchers compare void catalogs with CMB maps, weak lensing maps, and galaxy surveys, they find links that reach across very broad angles. Some are exactly what late-time gravity predicts. Others seem to extend farther than simple models expect, suggesting that the physics shaping voids drew from processes that acted on near-horizon scales early on. The safest course is to add data, fill in the redshift range with deeper maps, reduce noise in polarization, and refine lensing reconstructions so that projection effects mass along the line of sight that can mimic or hide a feature are better controlled. There are even proposals that tie voids to the Higgs field, the field that gives many particles their mass. If, during the early universe, the Higgs sat briefly in a slightly different state in some patches, the masses of particles in those patches would shift a little. That would change how gas cooled and how halos formed, possibly suppressing structure enough to leave long-lived basins. To test such a bold link, cosmologists look for precise, correlated fingerprints, a certain pattern in void sizes, a certain phase in CMB oscillations, and tight limits from particle physics experiments that keep the scenario anchored to lab results. None of these paths has won yet. What the Boötes region gives is leverage. Its size, cleanliness, and rich set of independent probes, galaxy counts, motions, weak lensing, dust and gas tracers, CMB temperature and polarization allow models to be tested many ways at once. A successful theory must match not only the emptiness, but the shape of the boundary, the small internal strands, the growth rate through time, and the way ancient light is altered along the sightline. As the void family grows and maps deepen, the comparative method gains strength. Voids at different distances show different stages of evolution. Young voids teach how basins start. Mature supervoids like Boötes show how they plateau. By stacking signals from many voids, observers pull faint effects above the noise, then turn to an extreme case like Boötes to see whether the same rules hold at the limit. Cross-checks reach beyond light. Fast radio bursts carry measures of the thin plasma they cross. Their slight delays can trace underdensities. The hydrogen 21 centimeter line, mapped over wide swaths, can reveal where neutral gas avoids or threads a basin at earlier times. Together, these tools make emptiness measurable in a dozen complementary ways. In that framework, the early universe questions become concrete. How smooth were the first seeds on the largest scales? Did inflation run in one simple mode, or in stages with brief features that left behind preferred sizes? Is dark energy fully uniform, or does the history of vacuum energy carry tiny, environment-dependent scars from inflation's quantum fluctuations? Do gravity and the dark sector behave exactly the same way in the deepest basins as they do in average space? The Boötes Void does not answer these on its own. What it does is set tight boundary conditions that any answer must respect, and it does so across the widest canvas we can currently trace. Cosmic voids may keep marks from the universe's first instant, when quantum rules set the stage and then handed off to classical physics. In that very early time, when the whole observable universe was smaller than a particle, random quantum jitters filled space. Inflation, the brief burst of near-exponential growth, stretched those tiny jitters to huge scales and then froze them. Later, gravity turned the slightly rich patches into clusters and filaments, while the slightly poor patches relaxed into broad basins of low density. A supervoid like Boötes can be read as a fossil of that first pattern. Quantum theory says even empty space flickers. Virtual pairs of particles appear and vanish too fast to see. During inflation, those flickers were pulled apart and could no longer cancel. Some became real ripples in matter and light, if the process differed slightly from place to place. Underdense regions today could bear that difference. The unusual size, clean interior, and brisk local expansion of Boötes make it a good candidate to test whether early-time quantum effects left special fingerprints in the thinnest parts of the universe. One proposed fingerprint is long-range entanglement. Entanglement links systems so that knowing something about one tells you about the other, even when they are far apart. Inflation can stretch such links to cosmic distances. If a large void and a distant region are still weakly entangled, their structures might show tiny, matched quirks. In practice, the way to look for this is not with a single pair, but with statistics correlating patterns in galaxy maps, weak lensing maps, and the cosmic microwave background over very large angles. Any excess correlation beyond what late-time gravity can make would hint at a quantum origin. The CMB itself acts like a screen that holds a record of the first conditions. Temperature and polarization patterns can be treated like a cosmic hologram because they encode information about the early quantum state in a two-dimensional way on the sky. Large voids modify that signal gently as photons cross their slowly changing gravitational landscape. The result can look like faint interference, cool and warm patches, small twists in polarization, slight lensing that shears the background's grain. None of this proves quantum entanglement on its own, but together these signals set limits on how strong early-time quantum correlations could have been. Some quantum field models go further and allow the energy of empty space, the vacuum energy, to respond to the environment. In very underdense zones, the vacuum could act as if it sits in a slightly different state, with an effective pressure that pushes matter out more readily. In plain language, the push of space would have a tiny regional tilt. Voids then become clean places to test whether such a tilt exists. If the interior expansion runs a little faster than average and the lensing signal remains very weak, the numbers can be compared with models where vacuum energy varies by a small amount. A related clue comes from super-horizon correlations in the CMB. We see temperature patterns that extend across angles larger than the distance light could have traveled by the time the CMB formed. That is one of inflation's basic successes. Quantum fluctuations made when regions were once close were carried far apart during inflation. Voids provide another way to check this story because their lines of sight cut broad cones through space. If their CMB signatures line up with those very large angle patterns, it supports the view that quantum mechanics really did act on cosmic scales. Quantum uncertainty adds a simple, intuitive piece. The uncertainty principle says position and momentum cannot both be known perfectly. Early on, that fuzziness applied to density as well. You cannot set every patch to the same precise value. Inflation stretched that fuzz into the initial map of slight highs and lows. Voids are places where the low stayed low. In that sense, their emptiness is a macroscopic echo of microscopic limits. Some theorists describe voids as quantum scars, a metaphor borrowed from wave physics. When a quantum system settles into a classical state, traces of the wave history can remain in special regions. Carried to the early universe, the idea is that the big wave function that described everything collapsed into the classical pattern we now see, leaving behind rare zones whose properties still reflect that transition. This is not established fact. It is a working image that motivates tests. The tests are the familiar ones. Measure growth rates, lensing, polarization, and the motions of the few internal galaxies, and ask if one consistent early time story fits them all. There are even proposals to use voids as amplifiers of delicate quantum effects. A deep, quiet basin has less ordinary matter, fewer strong magnetic fields, and slower plasma turbulence. That clean setting might let weak signals, tiny correlations in photon arrival times, small frequency drifts, minute phase shifts in radio waves stand out more than they would in crowded space. Quantum tunneling, the ability of systems to cross classically forbidden barriers, has also been suggested as part of the early sorting of matter, though no direct evidence exists. If many tiny tunneling events favored flow out of certain patches during inflation or just after, the long sum could contribute to lasting underdensities. These ideas demand better data. New and future observatories are designed to supply it. The James Webb Space Telescope has already begun to pick out ultra-faint dwarfs and star clusters in low-density environments, systems that earlier telescopes missed. Such finds tell us whether small halos in thin regions can still make stars, and how their stellar populations differ from those in busy filaments. Giant ground-based telescopes with mirrors larger than 30 meters will resolve individual stars in void galaxies much farther away. With that detail, astronomers can build color magnitude diagrams to date star-forming episodes and track chemical histories in isolation. Space-based gravitational wave detectors, such as LISA, will listen at longer wavelengths than ground detectors can. If primordial black holes, or cosmic strings, are more likely to survive in quiet zones, voids are good directions to monitor. A steady background of low-frequency waves passing through or near a large, clean basin would be lensed differently than through a cluster. Mapping that subtle effect demands patience, but it is a clear prediction to check. Radio arrays spread across continents are mapping the 21-centimeter line of neutral hydrogen over vast volumes. That line traces cold gas, even where it does not form stars. In voids, such maps can reveal whether hidden reservoirs sit along faint internal threads, whether gas truly avoids the interior, or whether there are pockets of material too dim to see in starlight. As sensitivity grows, tomographic maps, full three-dimensional slices, will show how gas and emptiness braid together at different times. Next-generation CMB missions will push temperature and polarization sensitivity to the limits set by cosmic variance, the natural statistical floor. With sharper maps, the small lensing and scattering signatures made by large voids become cleaner. Combining those with galaxy surveys lets researchers reconstruct the full mass along each line of sight, not just the visible part. That improves measurements of how fast the interior expands relative to the walls and how the boundaries shape changes with time. Neutrino detectors buried deep underground or under ice watch for faint flashes from rare interactions. If a dark sector exists with particles that talk to neutrinos more than to light, an excess from the direction of a large void would be a notable clue. So far, the sky looks even, but long integrations raise the chance of spotting a pattern. Dark matter experiments now also plan with voids in mind. The idea is not that detectors sit inside a void, but that voids act as control fields. If dark matter decays or has very weak self-interactions, the cleanest test is to compare sightlines through dense walls with sightlines through deep emptiness. A tiny spectral feature or a small excess in a specific particle channel that appears only in one environment would be hard to explain with ordinary astrophysics. Exascale simulations supply the theoretical backbone. They now include more realistic gas physics, star formation recipes, feedback from black holes, and, in experimental runs, small dark sector couplings or environment-dependent vacuum energy. For voids, the targets are clear. Match the size distribution, the cleanest interiors, the thickness and motion of the walls, the number and ages of internal dwarfs, the weak lensing signal, and the CMB imprints all at once. Models that fit clusters but fail voids will not do. Both sides of the web are part of the same story. Future X-ray missions with much larger collecting area will search for thin, hot plasma spread across void interiors. Temperature and density maps would tell whether broad, slow shocks from large-scale flows heat the gas, or whether the few active galactic nuclei along seams provide enough energy. If the gas proves cooler than expected, that would reinforce the picture of gentle outward flow with little compression. Precision astrometry measuring positions and motions of objects with micro-arcsecond accuracy adds another piece. Tiny, coherent drifts in background galaxy positions across a void's face, measured over many years, would reveal the pull of the walls and the lack of pull inside. The effect is extremely small, yet it is in reach of planned missions. Such direct motion maps would cross-check redshift-based flow models without relying on galaxy brightness or color. Large surveys will make void catalogs that are statistically complete across wide redshift ranges. Millions of identified basins, each with a measured size, shape, depth, wall thickness, and local environment, will turn rare features into well-constrained distributions. Stacking many voids together raises weak signals like small CMB deficits or slight lensing shears above the noise. Comparing stacks by size, age, or neighborhood then tests whether the rules that Boötes seems to follow hold across the population. Multi-messenger campaigns bring all channels together. A radio map may show a faint internal filament. An optical survey may find tiny galaxies along it. An X-ray stack may detect thin, hot gas nearby. A CMB lensing map may trace the mass ridge. And a gravitational wave watch may place limits on any compact objects along the same path. No single signal tells the whole story, but together they close loopholes and narrow the space of viable physics. There is also a horizon in instrumentation. Quantum-enhanced sensors, devices that use squeezed light or entangled states to beat classical noise limits, are beginning to enter astronomy. If they mature, they could measure tiny phase shifts or timing drifts in photons that have crossed large voids. While speculative, such techniques are exactly the kind of step needed to probe whether early time quantum information left any measurable residue in today's large-scale structure. Across all of this, the role of Boötes stays practical. It is a large, clean case with multiple independent probes already in hand. It anchors the high-end tail of the void distribution and sets tight requirements for any model of the early universe: dark energy, dark matter, and gravity. Its few internal galaxies give age dating and chemistry in isolation. Its boundary offers a sharp, well-mapped interface where flows, lensing, and redshift can be compared directly. Its CMB line of sight provides a long, simple test path through an evolving underdensity. The broader questions sharpen as measurements improve. Do voids simply reflect Gaussian inflationary seeds plus ordinary growth, with Boötes at the extreme of a long tail? Or do they require small changes to the early power spectrum? Is vacuum energy exactly constant? Or does the deepest emptiness expose a slight environmental shift? Do the motions at the edge match the lensing signal with the precision general relativity demands? Or do small, patterned departures remain after systematics are removed? Are ultra-faint dwarfs inside voids true galaxies with dark halos? Or are some unbound stellar associations? Does neutral hydrogen avoid the deepest cores completely? Or do we find cold clouds along ghost filaments too dim to light stars? Step by step, the work converts those questions into numbers. Growth rates in percent per billion years, wall thickness in tens of millions of light years, lensing convergence values at the parts per thousand level, polarization spectra with error bars that approach the cosmic floor. With that, the speculative links to quantum origins become testable. Either the patterns line up across independent probes, or they do not. Either the deepest basins behave like scaled versions of their smaller cousins, or they point to physics that acts only at the edges of our current maps. In this way, cosmic emptiness becomes a tool. Voids set the boundary conditions of structure formation, mark where the dark sector has the most room to act, and keep the earliest signals from being overprinted by later, noisy processes. The Boötes Void, by size and simplicity, sits at the center of that effort. As instruments gather finer data and simulations fold in richer physics, the region's combination of thin interior, crisp walls, faint internal strands, and gentle CMB imprint will continue to serve the same purpose: a precise test field where ideas about inflation, quantum vacuum, dark energy, dark matter, and gravity must meet the same sparse, stubborn facts.